Hold on. There we go. Go live. There we go. You guys can see my screen.
Yep.
Very cool. All right. So today we're going to be talking about tries. Some people might call them trees. Like technically, that's the right pronunciation for them. I'm going to call them tries today because it's just going to be too confusing to talk about them and trees at the same time. So, what is a trie and why do we care? So, a trie is what we call a prefix tree or a digital tree. It is a data structure for locating keys in a set. It is sort of like a hash map in that regard. It kind of looks like a tree. It has one key difference. A tree will store elements in the node. A prefix tree will store elements based on the position of a node in the tree. The actual data of the trie is being stored in the edges instead of the nodes. And for those of you who are unfamiliar by nodes, I just mean uh, like the particular spots on a tree, and by edges, I just mean the parts that connect them. So if you look at this trie that I have on the right, you can see that each of the nodes don't actually represent anything by themselves, but each of the edges between the nodes actually represent a sequence of characters. And this can be used to have a sort of quick lookup for certain strings. So for tries, there are certain ways that a key is associated with a node. Instead of having nodes containing elements, as I said, we consider the path from any ancestor node to the child node, and that is the element that a particular node is associated with. The path consists of edges, as I mentioned before. The edges are associated with some sub-element of a key. Most of the time, the sub-element is going to be a character, and the key is going to be a string. This is why you'll often find tries being used in dictionaries and suffix calculations and word lookup. So now that you know what a trie is, let's talk about the implementation. It's basically nodes with child pointers, so basically trees, but not quite actually. So no, by nodes with child pointers, I mean for any given trie, you're going to have an alphabet of some sort, and the naive implementation of this is going to include every node having an array of child pointers representing each letter in that alphabet. This is very inefficient actually, and it kind of beats the point of having a trie because you're wasting a ton of space. For example, 26 letters in the English alphabet. Once you get to a trie of depth, say 20, you're already past the known limits of having RAM in a computer. It gets even worse if you start using bytes. You have 256 letters in the byte alphabet. This is basically all the numbers between 0 and 255. That's literally 1 kilobyte per node. You literally don't even have to go to 20 before you've just exhausted the world supply of RAM. So the way we improve this is we consider the fact that nodes near the bottom of the tree don't have as many children. So we waste a lot of space and we start looking for ways to sort of either reduce the amount of space that each node uses or find a way to decide when or when not to use as much space per node. So here are some improvements that we could use to make our trie faster. The first is called a ternary search tree. And the idea for the ternary search tree is that each node has three children. The first node is the middle child, the second node is the lower child, and the third node is the higher child. The middle node is going to correspond to the next letter in a sequence. Uh, and then the lower child and higher child are both going to represent the start of another sequence of nodes. The lower child is going to represent the start of another sequence of nodes that has a value that's less than the first one. And the higher child is going to represent a sort of the same thing except for a higher value. This is pretty efficient because this lets you sort of recursively get rid of the amount of memory you use. So it's not like a constant decrease, like a factor that you're decreasing it by. It's actually like the growth rate of the memory usage decreases by a lot when you use it like this. Another way, when you're using somewhat small tries. You could also just use a bitmap. And for those of you who aren't familiar, a bitmap is basically when you take say, a 32-bit integer or something, or a sequence of 32-bit integers, and you just decide whether the zeros or ones in that integer mean something. So, for example, if you look at this illustration that I have down here, you have each zero representing a white and each one representing a black. And you could store this as 1, 2, 3, 4. This is 10 by 10. So this would be, you could use two long integers to store this instead of using like an array of 100 individual integers for like black and white colors. And that's an 8,000-fold increase in space efficiency between 1 kilobyte and 256 bits. So you can see why this makes it a little more feasible to use tries in the real world. Now that we know how to implement them, where can you use tries? So first and foremost, probably the most obvious usage for them, you could replace a hash table with a try. This because a try is essentially just a lookup tree. Uh, you sort of traverse down the tree searching for the next character in an element. If there's no child node that has that element or has that character, then you know that it's not contained in the table. And if you get to a leaf node, then you know that you found an element. And then at that leaf node, you can store the actual element itself. So this is good because it guarantees a lookup time that is proportional to the length of a key, as opposed to a lookup time that's proportional to the number of elements. Uh, for those of you who aren't familiar with hash tables, sometimes if there's a lot of collisions in a table, then it will have to basically search through all the elements linearly, just going through and trying to find where it's been stored. And that takes a lot of extra time. It's so speaking of collisions, there's also no collisions. You don't need to use buckets at all. So there's no, hacking some linked lists together and throwing them into an array to make sure that there's no collisions. You don't have to worry about a hash function, and you could even have a try be ordered. Um, Now, the reasons not to use a try instead of a hash table, it can be slower on average. Sometimes if you're using odd keys, such as floating point numbers, this can result in long chains of semi-useless prefixes. This is because there's a lot of entropy in floating point numbers, so there's not really a lot of common subsequences between them, so you're just going to end up with a bunch of individual sequences. And it also may require more memory, as each character of a search string must be allocated. For a hash table, you could just have the string itself be allocated and have that mapped to a value, which you use your hash function for. In this case, you have to have, as we mentioned before, your pointers, and you have to have your path down the tree. So that makes it a little more memory intensive for some tasks. Another, probably the most common use of tries is as a dictionary. And this can be used for all sorts of things. It can be used for predictive text. If you ever use the phone and you've typed something in and then it's suggested what you want to type, they use the try to do that. It can also be used for autocomplete. Similar idea, basically. Uh, if you're writing something and it goes down a path that only has one leaf node, then uh, the software can kind of determine that you're writing this particular thing, and it can complete that for you. It could also be done for approximate matching. You could travel down the tree as far as you can, and if you get like a certain distance down the tree, you could, sort of have a heuristic and have that represent your, uh, approximation of matching something. It can be used for spell checking. Actually, it's almost exclusively used for spell checking is exclusively done with tries. And it can even be used for hyphenation, which is a really cool sort of subproblem where you determine which words need to be hyphenated in a sentence. Whoops, sorry. So here are two problems. The first problem is just implementing a try. The next problem is actually like a really hard problem, but it is a very good try problem. If you could solve it, then you'll know tries in and out. I'm just going to walk you guys through my solution to the first problem. So can you guys see the leak code, or is it still showing the presentation?
We can see it.
Okay, good. So in this particular problem, It just asks you to implement a try and have some particular functions in it. The functions it wants a constructor, which isn't really that interesting for this problem. It also wants you to be able to insert a word into the try. It wants you to be able to search for a word in the try. And it also wants you to see if there's any prefixes that are contained in the try. So this is my solution for it. Uh, you can see we're just doing some C++, like, shenanigans up here. And then we get down here, and what we're doing is that we're just checking through each character in the word's sort of subarray. Uh, we're checking through each character in the word, and then we're going through the subarray of the node, and we're seeing if if that next character is contained in the node's next, in one of the edges to another node from that try. We continue downwards, and then we just set the node to the next one, and then we can determine whether the node is in the tree. Because if we get to a leaf node, then we're not going to be returning a. Is this right? Sorry, yeah. So we're not going to be returning true. So this we're not going to be finding a word in that. And then if we do not get to a leaf node, then we know that a new word has been inserted. So we'll just have that node inserted into the try. Now for this next one in the search, it's essentially the same idea, except instead of worrying about adding stuff to the actual try, we're just continuing down the try and seeing if we get to a leaf node. If we don't get to a leaf node, then we know that we haven't uh, actually gotten anywhere with this try. This word is not contained in the try. And then we're returning false because, uh, and if you're curious what this means, this here is just if the edge doesn't exist, then that's just going to return true for a non-existent edge. So we're returning false in that case. We're just continuing down, checking each character in the word, seeing if it's contained in that particular node, and then we're returning whether it's a word or not. Um, Lastly, starts with it's the same idea, except we're not going all the way to a leaf node. We're just traveling down the tree. And if we don't make it all the way down the tree, or we get to a node that doesn't have any edges or doesn't have an edge which is contained in the characters of the word, then we're returning false. Lastly, this part is just, more just initialization shenanigans. And as you can see, this runs for the test code. And if we submit it, we could also see that it matches yeah, there you go. It passes all the test cases. So I'll send these problems into the chat. You guys can maybe give a look at them yourself, see if you could solve them. Maybe, have a shot the second one. I definitely had some trouble with it, but if you could solve it, that'd be very impressive. It's okay. So I was hoping no one would ask that. Let me pull it up. So real quick, let me just send these into the questions part of the weekly workshop chat. So the second one, let me see if I could describe this because it's a little. Oh, it's good that my code isn't being shown here. I thought for a second that I was going to show the code from when I was trying to solve it before. But so the idea is that you have this board of characters and a list of strings, and what you want to do is determine which strings are contained on the board, and you want to do this within a particular time constraint. So this includes horizontal and neighboring cells. So basically, you just want to go through and determine like whether there's any words that are contained in this. So let me, yeah, here we go. So real quick, you walk through. So if you started from here, right, you construct a try, and then you'd use the try. So you construct a try, and your edges will contain E, T, A, and then you'd have A, T, E, O, A. Yeah, so you construct a try, right? And then you basically convert this board into a try, and then you traverse down the try using each of the words in the list of words that you're trying to look for. And then uh, I think that's it. I didn't really get it working, so I don't know if I'm missing something, but I think the idea is that you basically initialize a try and have it run through basically all the words and see if they're contained in this board. And like instead of having like adjacent and vertical edges, you just like have explicit edges with like E as the downward edge and A as the rightward edge. Hopefully that makes sense. I don't know if I'm doing a good job of explaining it. Sort of. So the nodes aren't, yeah, the nodes aren't the squares themselves. So the nodes could be thought of maybe as like the edges of the squares, and then like each edge can be thought of as being like, it's like if you started here, then you went like here, and then this would be an edge, and then you'd have a node here, like at the corner, and then this would be an edge for E, and etc. Yeah, it's tough. If anyone solves it, I mean, please tell me about it. I mean, I would love to hear about your solution because it's really kind of a tough problem. And lastly, thank you for listening to my presentation. And here's a list of words. They're all over the place. Doesn't really have anything to do with trees, but or tries, but it does have to do with strings and stuff, and that's what tries to use for it. So thank you.
Sticks is the one that knows. He's the only guy, the person that knows.
I am.
Yep.
I'll let Paul know when I decide.
Problem. 8:30. 8:30. Aren't the problems due tomorrow, Paul? Ooh.
Let's go.
Goodbye.
Thank you.